Okay. So we continue with the discussion on Liouvilles theorem in this class. And this is basically taken from Kardar section 3.2, page 59. But there is also a slightly different treatment of Liouvilles theorem in the Rife. I think it's in the appendix, and that has a better physical insight. But anyways, with that background, it's also there in every book possible, Wang and Patria, and so whichever is your favorite book. But this is basically taken from Kardar section 3.2. So the focus is that we are going to consider a phase space volume. So there's a macro state, and for that you have which is specified by the momentum degrees of freedom and space degrees of freedom. And if there are n particles and you are in 3D, then you need to specify 3n momentum degrees of freedom and 3n position degrees of freedom to specify a microstate. Now we are looking at a very small volume, d3q. So basically D3, Q1, Q2, and so on and so forth up to 3n, except that this is 6n dimension, and then similarly P1, P2, P3, dP3n. And we're going to look at how many microstates or phase space points are there within that volume. And next of all, we are going to think of how these phase space volume points are going to evolve as a function of time. You could consider, if you wish to do, that basically a same system is at different phase space points within this small volume at different points of time, and you're looking how all of them proceed, how all of them evolve in dt. If that is too confusing for you, what you could also think that you have a capital Q number of independent you have macro systems. Each of those macro systems, the first corresponds to the same phase space volume, and suppose each macro system is in different is occupying a different microstate. So each of those Q systems is evolving from one microstate to the other, and thereby they're exploring different points in phase space. The second macro system is at a certain instant in time is occupying a different microstate, and it is evolving in time. And if you have capital Q number of macro systems, each of which consider correspond to a large number of microstates, the same number of microstates, then out of these Q macro systems, dq number of macro systems at a certain point in time will be within this small volume in phase space, and that will be representative of the number of points there are within this small volume of phase space. And we are looking how these dq number of macro systems corresponding to dq number of microstates which are within this volume, how they're evolving as a function of time. The q minus capital dq number of systems, macro systems, are in different microstates which are outside this phase space volume. So we are interested to discuss the phase space density, right? How many phase space points are there within this volume, and if you like, dq will be proportional to the number of phase space points within this certain volume. So basically this I mean, if there's a certain number of phase space points you are specifying q macro systems, a small number of them will be in this volume, and that will be proportional to the number of phase space points that you have within this volume. And rho is the phase space density, number of phase space points, number of microstates possible within this small d3q, right? And so basically dq is the phase space density into I mean it's proportional to, but suppose you have enough number of macro systems so that each so you have the same number of macro systems as the number of phase space points, and then dq number of systems will occupy will be in each of these phase space points, and hence dq is proportional to the phase space density into the volume of that small into volume of that cube in 6n dimensional space, dq1 to dq3n, dp1, dp2, dp3 to dp3n. So it's a cube small volume in phase space, and the number of points will be the density into this volume, right? And that corresponds to the number of macro systems in the ensemble of macro systems which have position. This is in 6n coordinates. So position and velocity in volume d3q and d3pn, right? And since I'm specifying n here, this is a vector, this is d3, right? So this corresponds to q1, q2, q3, and that's why d3 qn and d3pn. And just to have an idea, just to clarify, that if you integrated rho over the entire volume of phase space, right, and that would correspond to, in the discrete sense, so there would be a certain number dq number of phase space points or macro systems, if you like, in d3q1 to d3qn into d3p1 to pn, and in a different volume of phase space you would have a different number of dq. Now you're summing over all of this, so basically you're integrating the phase space density over the entire volume of phase space, and that will be equal to 1. Why will that be equal to 1? So basically what you're going to do is normalize over the total number of phase space volume, right? Because density is defined the total number of phase space points, number of phase space points within a certain volume. Now you are integrating over all of that and normalizing by the total number of phase space points. So if you integrate over that, okay, so sorry, so this should be divided by q actually. So if you integrate over the density of phase space over the entire volume divided by the total number of phase space points, that will obviously be equal to 1 because in normalizing, right? So so what we want to show is that the phase space density behaves like an incompressible fluid. What does incompressible fluid mean? That its density doesn't change. That means that if a certain number of phase space points are there within a certain volume, d3q, q is 6n dimension, and d3p, then as the phase space coordinates move, as the systems move and occupy a different volume in phase space, the density is going to remain the same. That means that the volume, the modified volume element will have the same volume as that of the original element. So the density, the number of points per unit volume will remain the same as the system evolves as a function of time. But we really are talking of only Hamiltonian systems. So we are not talking about dissipative systems. We are basically discussing only systems which follow the Hamilton's equation of motion. And the statement that phase space density behaves like an incompressible fluid is the so-called Liouvilles theorem. And it's from here that we shall go to the concepts of, I mean, which will lay the foundations of a postulate of equal a priori probability. But we're really talking Hamiltonian systems and not dissipative systems. This is important to be kept in mind. I think I've repeated myself 3 times already. As I already said, just imagine few copies of a macro state. Each macro state corresponds to a point, to a phase space point in an ensemble, and dq copies of them are within a certain volume, dq1 into dp1. But though in this figure I have said dq1 and dp1 because that's what we can represent. We can represent an area here, but in general we are really talking of dq in 6n-dimensional space, phase space volume. So, and so many number of points are within this volume element. Uh, yeah. Moreover, if we are interested to calculate the expectation value of any quantity O, let's assume kinetic energy density, kinetic energy, or energy of the system, or momentum of a system, or momentum in the x direction of the system, then what we would do is basically, if the system is within this volume, this small volume d3q, d3p, where q is 3n-dimensional and p is 3n-dimensional, then we would take the density of phase space within that into the volume that would correspond to the number of phase space points which are there within the volume. And what is the value of that quantity we are interested in, O, say, when the system occupies these set of coordinates within this small volume. So basically the expectation value of O will be rho, the density of phase space at PQT, into O, the value of that variable when the system has coordinates P and Q within this volume, into integrated over all space, right? So suppose when the system is here, has certain different sets of coordinates Q and P, it has a certain different value of O, and so on and so forth. So you basically take the density, the value of that quantity when it has PQ value, and integrate over all space. So D3Q and etc. will correspond to the value when it is here, right? I mean, the number of phase space points into the value here, but then you are integrating over phase space. That's how you calculate the expectation value of any quantity. And now what we are interested to look at is look at the evolution of dq. So this shouldn't be n, but this should be q. dq microstates as a function of time. So these dq are within this phase space volume, and again here it should be dq, a small number, a small fraction of the full ensemble of points, and we are looking at the evolution of that. We shouldn't use n because n is being used in terms of the number of degrees of freedom, right? So I actually changed this to q, but I forgot to change it. So this should be dq, and this should be d capital Q, and so on and so forth. Now, for the points, so there are dq systems, dq points within this small volume, and they're going to evolve as a function of time, but they're going to obey Hamilton's equation of motion. So this small volume, so suppose this is, so this has some value q1, and this has value q1 plus dq1. So these points is going to evolve and occupy. So q1 is going to occupy q1 dash here, and q1 plus dq1, suppose, is going to occupy a separate q dash plus dq dash here, right? So all of these points are going to move to different points because they have evolved, because they are going to have different values of q1s and q2s and p1s and p2s as they evolve in time, and occupy a different volume element. So this q1 will become q1 dash, this if this was something else, q1 plus dq1 dash dq1, that would become q1 dash plus dq1 dash, right? So they would all move, and all the points will also move, and these are now occupying a different volume element in space. Now, what can we say? The question is, what can we say of this, the magnitude of the volume of these two different volume elements? So we're going to discuss that. So that's where we are heading. In general, we can write about dq, the number of phase space points, as the density of phase space points here into d3q1, so on and so forth, to d3qn, d3p1 to d3pn. Now, we are not at the moment trying to assume that the density of phase space is constant. We'll get that it behaves as an incompressible fluid. That's what we are after to prove. And suppose the same number of points, well, this dash shouldn't be here, but this dash should be here. Suppose it's a different density and it is occupying a different element in phase space. Now you could say that qi, so suppose this was qi, I mean, of course, there are different points, but so one of these points, they're going to evolve as Taylor's expansion qi plus qi dot dt, the rate of change of qi with time into dt, plus higher order terms where I can be 1 to 3n, and similarly pi dash can be written as pi plus pi dot, the rate of change of pi with time into dt, plus higher order terms where again I can be 1 to 3n in 3D coordinates. Now similarly, we could also say, so suppose this was qi dash and this was some other other point that has evolved here. This one point has evolved here. This point has evolved here, and so on and so forth. So we, just like we could talk about qi, how it has evolved, we can also talk about dqi dash. This is the difference in the coordinates which make up the volume. So this is like dqi dash, right? So this is one side element of that volume in 6-dimensional space, of course. So how has that evolved? So no, this is of individual coordinates, and when we write a vector, that's 6n dimension, and that will evolve as dq plus how qi dot is changing as a function of qi. So the value of qi dot here and the value of qi dot here at a different point could be different. So dqi, how much this length has changed, right, as the system evolves, is proportional to dq into how does qi dot change as a function of dq, right? Because this one evolves at a certain q dot, this one evolves at a different q dot, and as you change qi, how does qi dot change into dq into dt plus higher order terms? And similarly, thinking very similarly, we can also write dpi dash equal to dpi plus how does p dots change with pi into delta pi dt into higher order terms. Right now, del q dot. Now q dot can be written as del h del p, and p dot can be written as del h del q because they are obeying the Hamilton's equation of motion. We are considering only those systems which are Hamiltonian systems which obey the Hamilton's equation of motion, and in that case, dqi dp can be written as dq. So what we have done is taken this equation and taken this equation and extract out dqi 1 plus dq dot del qi into dt, And similarly here, that's all that we have done. So we have written out dqi 1 plus dq dot I dq dt plus higher order terms 1 plus del pi dot del pi. How does it change with pi dt and so on and so forth. So this becomes in that case del qi del pi 1 plus this term plus this term, because so basically this term multiplies with this term multiply with this, that gives the term between the two blue brackets, and if you multiply this term with this term, that is giving you terms order of dt square. So we're going to ignore all of that. Now this itself, if you substitute the q dot as del h del pi, and if you substitute p dot as del h del qi, right? So then it will be equal to 0. So these two terms cancel, and what we get in turn is dq dash dp dash equal to del q del p, del qi del pi. And similarly, we can do the same thing for 6 n-dimensional coordinates. And the consequence is that the volume element, the volume element, it has changed, the coordinates has changed, the shape might have changed, but the total volume element remains the same under time evolution. And since this, we are considering that the same number of points are occupying a different volume in phase space, so dq has to be the same. This quantity is the same as dq1 to dq d3qn. So this element of remains the same, and hence the same number of points are occupying totally the same number of volume in phase space, though the volume element has changed, and hence the density has to remain the same. So because the volume element value remains unchanged, the density also remains unchanged. So the product of the two gives the same set of phase space coordinates. So that is the essence of what we are discussing. And the next thing to discuss is this means that as the system evolves, in time, and as the system goes from one point occupying one set of phase space coordinates to the other, the density of phase space coordinates remains the same, right? So note, this is ddt, which means because the system is going from one point to the other and it's changing its also p and q values. So that also so as the system goes from one point, as evolves in time, it also changes its q values. So basically it's a different element in phase space, so each of the particle might have moved in different directions, right? But they're occupying the same volume. So this implies that the explicit dependence of rho. So suppose you're sitting at a certain point of time and you're looking at how rho is changing for the same coordinates. And at that point, of course, systems which were at a different point, they have come in, right? So remember, so we are really discussing phase space density does not change over time, even if the shape of the volume gets changed. And note the difference between del del t and ddt. Ddt is you're sitting on it, it has moved at a different, as a function of time, it has moved, and it is occupying different p's and q's. There, whatever the density is remains the same as that it was at time t equal to 0, right? So overall, the ddt has the space and momentum derivatives as well, and that does not change. The density does not change as the system moves in phase space and it moves in time. And this can be written down separately as minus del rho del t, I mean, you could write this as del rho del t plus this quantity, which is how does del rho change as you go along t? How does del rho change as you change q? And I goes from 1 to 3n, right? Equal to 0, but you have brought del rho del t on the other side of the equality. Right? So this implies this, and now you're saying that del rho del t, uh, if they're obeying Hamilton's equation of motion, so you have replaced p dot by del h del q, and q dot by, yeah. So I think here it is minus del h del q, yes, and here it is del h del p. So you have this minus sign which is sitting here, and p dot is minus del h del q, hence you have a minus sign here. And this quantity is nothing but the Poisson's bracket, right? And if rho is a function only of the energy, if the phase space density is function of only of the energy, uh, so, and if this Poisson bracket is equal to 0, it also means that at any point in phase P and Q, del rho del T also will be equal to 0. So it's not going to change. The phase space density is not not going to change as it moves in Q and P, but at any local point, at any value of P and Q, the phase space density is also going to remain explicitly time independent, right? So this means that, so if del rho del T equal to 0, so one can look at it in two ways. If this is equal, if rho is a function only of energy, then del rho del T is going to be 0 at each point in space. Is going to, there's not going to be any explicit time dependence. You can invert the problem and say that if there is no explicit time dependence on rho, if this quantity is 0, then the Poisson bracket of rho the Poisson bracket of rho and h has to be equal to 0, and that means that the phase space density is going to depend only on h. Rho is a function of h, right? Moreover, we have already shown that phase space, uh, so the phase space coordinates moves as an incompressible fluid, right? And now you are saying at an explicit point in time, there is no change. If rho is a function of h, which means that all over the phase space density is going to be remain the same if rho is decided by h. If rho is a function of E and nothing else, then E decides the density of phase space coordinates, and all over the density of phase space coordinates remains the same all over Q, P, and T, right? So if the density of phase space coordinates remains the same, then the systems can occupy any of these points. It's not that at a certain point, for a certain value of P and Q, there are more points. Then the system will spend more time for a particular values of P's, or let's suppose Q, because P is difficult to imagine. So for a certain set of coordinates, space coordinates, if this corner of the room had more, it had more phase space points, then the system would spend more time exploring those phase space points. But no, everywhere the density of phase space points is the same, right? So it will spend all its time, I mean, any point for any phase space coordinates, it will spend equal amount of time. There's no preference that it is going to spend more time for some at some coordinates in space and time. I mean, for some p's and q's. So all over it is the same. So the system is going to explore all of them equally. There's nothing to choose for because the density is the same, and that's where uh, that's how the consequence of Liouvilles theorem is. There's nothing in the dynamical equations for an isolated system. There's nothing in the equations of motion which will make a system choose a certain set of p's and q's preferentially over another set of p's and q's, because at each point the density remains the same. So it is going to spend equally any values of p's and q's, and it's from here that you say that, since the density of phase space coordinates is the same, there's nothing to choose from. So each of these phase space points have equal probability of being explored by this system. So this is the importance of Liouvilles theorem. Okay, so I'm going to end here this part.